Okay. Okay, last time we have discussed on directional derivative. Okay, and we have discussed on the functions of three variables, and the idea is still the same idea, which is the directional derivative we can write in a gradient vector of f and then multiply with the dot product of the unit vector u. Okay. Okay, let me go through a new section. This will be how to maximize the directional derivative. So maximize means that at what values that the derivative will be maximum. That will be the question. So how do we maximize this directional derivative? So first is we are looking at the directional derivative, the general equation. Okay. Now, if we look on dot product, if you look on this dot product, we can rewrite this with the property for dot product, which is having cosine theta. Okay, so the angle theta is between gradient vector and vector u. And maximum value of cosine theta is 1, right? So this. So theta will be occurs at 0. Okay, so the maximum of directional derivative is when theta is 0, and that is when uh, when the factor u has the same direction as the gradient vector of function f. Okay. Or simply we can write in a more official, we can write, suppose f is a differentiable function of 2 or 3 variables. The maximum value of directional derivative is the magnitude or the absolute value of the gradient vector f. And this x means that it's a factor. It is a factor. It's a factor. So it can be two variable. It can be 3 variable. Okay. So whenever you are asking, you have a question that asks to maximize the directional derivative. It means that you can just look on the gradient vector f, and then assume that the cosine is 1. So you just evaluate the value of the gradient vector. Let me give you a context on how we can apply this the theorem. Okay, if you want to write, I think the important thing is the first part here. That stated the assumptions for how to get the angle to be maximum. Okay. Okay, now let me give you a context on a question or example. Let t a function of 3 variables, and let this is be a temperature function. So at divided by 1 plus x squared plus 2y squared plus 3z squared. So this will be a function or temperature function in space equation, where the x, y, z, it's in the meter unit, and T will be in the degree of Celsius. Now the question is, in which direction does T increase fastest? At 1, 1, -2. And then when is the maximum rate increase? So first it's asking the direction, meaning the vector. They need to know where the direction is, the positions for the vector. And the second question is the maximum rate, meaning the value of the rate. Actually, it can be combined into one question, that this is going to be finding which one is the fastest, which is the maximum rate. Okay, the maximum rate. So it's actually same similar terms. Increase fastest, it means that it's the maximum rate. But the first question is asking the direction, which means that the vector itself. The second one is asking the value. Okay. So first, if we have this, okay, the key, everything you have in the equations, you need to have its partial forms. Okay. Now we need to get the gradient vector. Okay. So every time you are asking on how to find the directional derivative, you're going to write the gradient vector, right? The gradient vector, which is the partial x, partial y, and partial z. Now, if we look on the structure of the equation, we have the variables on the denominator. So that if we have this, then if we derive, this will be going to have 1 over negative 1 over x squared, right? So when we have this x squared, y squared, z squared, and we want to find each of the element or each of the variable, the partial forms, means that first, when you have the partial x, we are going to derive with respect to x. So x squared become 1 over, so we will have, so if we would like to write the whole thing here, so this will be 1 plus x squared plus 2y squared plus 3z squared, and then squared. And then we have negative 2x. And then we have another one, negative 4y. The same denominator. Yeah, we can also use the quotient rule to make this happen. Oh, 80, sorry. Multiply with 80. Forgot to multiply. Okay, we get this. And now we have, it's become 160, 320, 480. I think we can factorize 160. Go outside and factorize the denominator. 1 plus x squared plus 2y squared plus 3z squared squared. And the factor inside will be negative x, and then negative 2y, and negative 4, or 6, right? 6. Six, 3, 3z. Okay. Okay. Now the gradient factor at the point 1, 1, negative 2, we can input. So this will be 1 plus 1 plus 2 plus 4, 12. It should be 16, right? 16. So it should be 10. Should be 10 all squared. We will have 16, 16. So we will have 10 over 16 is going to have 5 over 8. And then this will be negative 1, negative 2, and 6. Okay. So meaning at this, at direction negative I, negative 2j plus 6k, this is increase fastest at this direction. Okay. And then the second question, the maximum rate, it's actually asking the value for the gradient factor. So we are going to find the results from the value. We will have 5 square root of 41 divided by 8. So this will be the maximum rate. Okay. Okay, any questions? Do you think the screen is delayed, or it's okay? I think someone need to mute that voice. Okay. Okay. Anyway, is my voice clear? Can you write in the chat box whether my voice clear or not, or is there any delay? Is there any delay on my voice or in the screen? Can you reply to the chat box? No, no delay, or it's clear, or it's clear. Okay, thank you. Okay. Actually, I have uploaded additional video for chapter 14. One video is about the exercise. I think around three, I think four questions exercise. And another video is about the last sections on chapter 14, in which I think we can just watch the video and then later have some exercise. Okay. So I will focus for today. I will focus on finishing this directional derivative and going forward to 14.7, which is the maximum and minimum value in partial derivative. Okay, okay, I hope you get a clear understanding on how to get the maximum directional derivative. Okay. The assumption is uh, by evaluating the gradient factor and finding its value, okay, and that is uh, the fastest or the maximum rate. All right. Okay, next section is about the tangent plane level surface. So let me move to the next page. Okay. Okay, so tangent plane to level surfaces. So from previous sections, we know that I think from 14.4 that you have the tangent plane equations, which is we can write as this, right? Okay. Now we can have much more general equations for the tangent plane, and we can actually using approach or using some method for the gradient factor. Okay, so through the gradient factor, we will know in much more clear way on how to write the tangent plane in more general. So let S be a surface of equation. Let's say we have x, y, z, three variables, and then equal k. So this will be level surface of function with three variables. Okay, let me put the illustrations to make sure that this is clear and understandable. Okay, so this is the functions. Now, as you can see, it has a point of P, our observation. So let P be a point of x0, y0, and z0 on S, okay, on surface S, and C will be the curve on S, that pass through pass through the point P, pass through P. Okay? And we can let the C as vector functions RT, okay, with parameter T. So we are going to connect the chapter 14 to chapter 13. So we are going to connect with the parametric equation for the vector functions xt, yt, and zt. Okay. And let, this is supposed to be C, and let this P correspond to the parameter T0, okay? Now, because C, okay, C, okay, the curve C, it is lies on the surface S. So we can treat the curve as uh, a functions or level surface of functions. Okay. If you remember what we did in the first introduction on the chapter 14, we are introduced on the contour, like when you have maps. Okay. If we look on from above, we can take this and we see, like, probably we will have like the contour like this, okay, and it's certain color will determine certain height, right, different height, okay, and this is actually applied similarly, okay, so we will have a level surface for each point of C. We will have each level surface. Now we can take the notions that because the curve C is on the surface S, then we can take the functions the level surface functions that equal K. We can derive this, and we can partially derive with respect to T to show that we will have this connection. So if this is if all x, y, z differentiable differentiable functions of t and f also differentiable, okay, and then we can have this chain rule. And then since if we look on this gradient factor and the r prime here, okay, we see this two from the dot product for these two, we can write that the gradient factor of f multiplied with dot product with the r prime t, this will be resulting 0. Okay, and then when t is t0, we can have r t0 as x0, y0, and z0. So the gradient vector at x0, y0, z0 multiplied with dot product with the first derivative of r at t0 is equal to 0. And this is actually the first step to derive or to develop the tangent plane. Okay, the tangent plane to the level surface. So it says that from here we can write the implications that the gradient vector of f at point B is perpendicular to the tangent vector. So at any level curve on the curve C, so if we are going to look here, so if we take another approach, maybe point here, this will be also getting the similar property, which is the gradient vector and the r prime is always orthogonal. It's always perpendicular. Okay. Now we can write. Okay. Now we can write from these equations here, from the dot product here, we can write in more clear. Let me precise some of the equations. Okay. Now the tangent plane from these equations, we can write that the tangent plane is so this will be the tangent plane, tangent plane equation. And the normal line, if you remember I think in chapter 12, this will be x minus x0 divided by x partial x partial y partial z. So if we have three variables, okay, function of three variables, and we know that we can define the functions in terms of level surface, then we can at least at some point we can write down the tangent plane. Okay, the tangent plane. Okay, let me give you an example on how to apply the uh, the method, okay, the tangent plane. Okay. Oh, by the way, you can write me an email if you want to know your score before I deliver the result for your midterm. You can email me and I will, if you want to know uh, directly. Some already emailed me, but I haven't answered, but I will answer later. But you can email me for your results. I will deliver later the midterm and also the key answer, the answer key. Okay, I will go to the next page for example. Okay, I hope you can at least okay for this this page, the key is this two. Okay, this is the key for the tangent plane. Okay. Okay, let me give you an example. Find equations of tangent plane. And normal line to the given surface at specified point, or maybe let me write a little bit down here, at specified point. So the a, let's start with x y squared c cubed equal 8. This is at 2 to 1, and the other one is a little bit complex. Let me just write it for exercise. 3 power of 4 plus y power of 4 plus c power of 4 equal 3x squared y squared c squared at 1 1 1. So let me give you a few minutes, a couple minutes for you to try by yourself, okay, by using the previous equations, previous method, and see how do you get the answer. Oh, before that, to be clear, okay, to be clear, the tangent plane means that the tangent plane on the point on the surface, but the normal line is different from the normal vector. Okay? The normal line means that the normal for the parametric, or we say the symmetric, okay, symmetric equation. If you talk about the normal factor is the gradient f. This is the normal factor, right? Because it comes out of the plane that we call the normal. That's the definition of normal, if you remember normal. So when we have this normal line, the question has normal line means you need to connect this normal line to the symmetric equations on the parametric. If you remember the parametric one. And why the name is using normal? Because it's using the so basically if you look here, this f at the bottom is from our gradient factor, right? Our partials. And our gradient factor is our normal factor. So it means that the normal line, our symmetric in the parametric definition, when we define with the direction in which the direction is our normal, we call it the normal line in the partial derivatives. Okay. So it's to avoid confusion. So when we have normal line, means we are going to connect with the symmetric equations in the parametric, if you remember the parametric one. Okay. Anyone got the answer for the first one? What's the tangent plane? If you have, you can write on the chat box. Okay, perhaps I will show you how to deal with this question. So first, every time you have the tangent plane, we are going to find the gradient factor. That is the key, the first key point. So find the gradient factor. Or maybe before that, the more basic one is to define a function. So we need to define a function. So let's define the functions as this. Okay. Now if we take the gradient factor, then we will have partial x, we will have y squared, z cubed, and then 2xy z cubed, and then 3xy squared z squared for partial z. And we will have at point 2, 2, 1, we will get this will be 4, 2, 2, 4, 4, 4, oh sorry, 4, 2, 8, so 4, 8, and then 6, 6, 4, 24, 24. Now we call this is the normal factor for our directions for the tangent plane. And then we can write the tangent plane as 4 x minus 2 plus 8 y minus 2 plus 24 z minus 1 equals 0, and we can solve this, and I think this will be 4x plus 8y plus 24z, negative 8, negative 16, negative 24, negative 24 is negative 48, or we can write equal to 48, or we can simplify it, become x plus 2y plus 6z equal 12. Okay, the normal line, you can write the symmetric equation. symmetric equations of we can take this is 1, this is 2, this is 6. So we can take x minus 2 divided by 1, y minus 2 divided by 2, and z minus 1 divided by 6. And we can say that this is our normal line. Okay. And I believe you can try this by your own. Okay, you can try yourself. If you have some confusions, you can discuss with me later on. Let me write what's the implications for the gradient factor and what is the property in the summary. Okay, suppose that the gradient factor is not equal to 0. So the directional derivative we can write as this. Okay, this is the key points, 3 key points in the gradient factor that you need to be aware of. And the second one, the maximum rate, okay, as we mentioned before, is the absolute value of the gradient factor. So you need to find the value of the gradient factor. So you need to rewrite the factor forms and then write in terms of the magnitude. And then you can also have the third implications, that is the gradient factor is perpendicular or orthogonal to the level curve or level surface. Okay, and then finish the directional derivative. Okay, any questions? If you have questions, you can write on the chat box. Or perhaps one additional notes. Okay, we discussed in the 3 variables, right? But what if we look back, okay, what if as in function of 2 variables? So let's see equal function of this two variable xy. Then our xyz, this will be, we can write as minus z. So the gradient factor is partial x, partial y, and 1, or negative 1 because it's minus z. Now the tangent plane from here, okay, we are going to connect this with previous tangent plane. This will be x minus x0 plus f partial y minus y0, and then minus 1, and then z minus c0. And this is perfectly similar to what we have done in 14.4. Okay, so basically what I'm doing here is to show you that what we did here using this gradient factor, it's much more global. So you can use this for any situations, as long as you can define which one the functions and which one is the function of level surface. Okay. So we are going back to what we have in 14.4, right? Same structure. Okay. I think this is also important, so you need to keep in mind. Okay, so because uh, there's a lot of uh, content, and if you can connect all the relations for all the contents, I think that will be helpful for your study in the future, right? Okay, now the next section, this will be about the maximum and minimum value on the space curve, the three dimensions on the partial derivative. Can we have more? How do we make? How do we find the maximum value, minimum value, and is there any critical points like the one that we are have in the calculus one? So we are going to explore in 14.7 max and mean values. So recall that in calculus 1 we have, how do you know the point is maximum or minimum? We are going to have at least 2 points, right? The critical point through the first, usually we can use the first derivative test. We know the function increasing, decreasing, right? And the second is we know the second derivative test, in which we have the concavity. And sometimes we can also find the inflection point, the point that where the concavity changes from upwards to downwards or from downwards to upwards. So we are having the first derivative and the second derivative. Now what will be the difference in calculus 2? We will have the function itself is multivariable, so it leads to two variables x1. Right? Now first, if we have these two variables, if we can imagine in a graph or in a picture that we will have at least these illustrations, okay, to give you much more sense on how to denote that which one is maximum, which one is minimum. And I think the definition is similar with the calculus one. So if you have a domain and if you have the point that is maximum on all the domain, then that point will be the absolute maximum. And if it is lowest, then it will be the absolute minimum. And if it is having uh, some, if you see from some angle that it's going increase and then going to decrease, this point will be the local maximum, and the otherwise the other one will be the local minimum. Okay. So of course, if we are talking on the absolute maximum or minimum, we are talking on the set of domain. That should be clear. So first, let me write. Maybe write function f has local max at x0, y0 if x is a disk centered at x0, y0 such that at the function x0, y0, at the x0, y0, the function is I think this is pretty intuitive. It should be higher than the other function for all x, y in the disk, which means that the disk is actually our restricted area. So if we restrict area, like here, if we restrict area just this circle, then among the circle, the point will be having this one is the maximum one, and we say that it's a local maximum. And it will be having a local minimum when the function at that point is less. And of course, the absolute maximum is when the f is higher for all points in domain. And absolute minimum for all points in domain. I think the words is not as much as important as the definitions, but I think the notion that if we take this, all this for, and or if you look on the picture here, I think it's already obvious, okay, that which one is the absolute minimum, maximum, local maximum, minimum. Okay. Okay, but if we can have a restriction area, which we call the disk, okay, how do we take in more concise and precise, how do we point out this maximum is maximum or this the minimum is minimum? So the way we are going to observe that is by have some boundary. So we have like a cage, like a box. And this box will be our main observations. Okay? And from this box, we are going to determine whether this is going to have the maximum or minimum. And we will have another theorem we call the extreme value theorem. It's similar to what we have in calculus 1 actually. So before we have the bounded set in 2 dimension. We just have this, and then we have some functions like that, and then we know that which one is maximum minimum, right? Directly from the 2 dimension space. But now we have at least 3 variables, 3 axes, and let's say we have functions here. So what we are going to do, we are going to have some set of blocks to restrict our functions inside this box. So we will have a 3 dimension space like that. Okay. Wait a moment. Okay, sorry. Okay, let's continue. Okay, so this is we call it the bounded sets, okay, or the boundary to restrict our function. So by definitions, the extreme value theorem is saying that if the functions of two variables continues on, okay, a closed and bounded sets of R, then the function has both absolute maximum and absolute minimum. So this is, I think, uh, I'm not sure if you can imagine this, but whenever you have any functions that you can think, any working functions, they are all having at least maximum and minimum, and they will have the absolute maximum and absolute minimum. If not, I think it's not a function, right? You can imagine the functions that have changed. Yeah, it must be right. And from here we can also look on the Fermat theorem. If you still remember the Fermat in the calculus 1, it's about the local extreme value. So if f has a local extreme, max or min, at point x0, y0, and if the first order of partial derivative of the function f exists at those points, then as implications, the partial x0, y0, this will be 0, and the partial y, x0, y0, this also will be 0. This will settle the critical points at x and y. But critical point is not always when this partial x is 0. We can also have critical points, if you remember calculus 1. If the one of this doesn't exist, we can also call them a critical point. So first thing is to equaling these two partials, partial x and partial y with 0. And we can find the critical point. So the x0, y0, this will be related to critical point. Okay. So I hope you can make some connection with calculus 1, okay, some reference. The Fermat, if you remember the Fermat theorem, it's also saying the connections with the derivative and the maximum and the minimum. and for specifically the critical point. Okay. Oh, by the way, if you have, uh, because we will have, I believe we will have a quiz next week for chapter 12 and 13. I think if you are not available next week, um, for example, if you tested a positive for COVID, you can let me know. Okay, you can write me an email. Some students already write me an email before, so that's why this week I need to maybe have a online class for a while. Uh, Next week we can start to have offline class, but please, if you have some symptoms or if you have you checked that using the rapid test, or if you check the PCR and you are detected positive, then I think you can just inform me, and whenever we have an exam, we can have some postpone for those students, okay, who are not available during the exam. Okay. And I will also have some survey at the end of the lecture today. I hope we can have more. Yeah, because I think today's the rate is quite high, um, but it's not as severe like last year. And the school actually already opened um, there's no tracking system, I think, in our school, so we can actually doing an offline class, but I need to observe some problems this week, so we will have an offline and maybe an exam next starting next week. Okay. Okay, let's go back to the lecture. Okay, so the Fermat theorem. Okay. Okay, if we go to some example to imagine how this works, okay, the action value theorem is actually not too complicated as you might think. For example, if we start from here, okay, this graph, this is the quadratic surface of the paraboloid. So this will be the equations. Okay, if we start from here, and if we would like to observe the maximum and minimum value, we can start with the partial x. This will be 2x minus 2, and then partial 1. This will be 2y minus 6. Okay, and if we are having 2x minus 2 equals 0 and 2y minus 6 equals 0, in order to find the critical points, we are getting that this is equal not x, 1. So at 1, 3, seems that this will be a critical point. And I think that that's true. And if we look on how it goes in the picture, at x equal 1 and y equal 3, it's having the minimum point here. Okay. And if we complete the square and see for ourselves with the quadratic surface. If you remember the quadratic surface, and we shifted um, the vertex, so we can write down. Okay, we can solve this, and we find divide by 2 plus 9, right? So we can complete the square. So we will have plus minus 9 minus 1, sorry. Minus 1, so this will be 4, right? Yeah. So we will have this, and from here we can actually confirm that at x equal 1 and y equal 3, this will be the vertex, right? The vertex of paraboloid. So at this f1, 3 equal 4, this will be the local minimum. And in fact, if we consider all domains, this will be the absolute minimum. We can consider this as absolute minimum. Okay, just to show you how it is. However, another quadratic surface that has different equations or different structure in terms of the graph. If we take a look on the quadratic surface of y squared minus x squared, this is we have hyperbola and we have the paraboloid. So it's hyperbolic paraboloid. And if we draw, if you remember the shape, this will be the shape. Now the interesting part here, if we try to find the partial x from this one, we will have negative 2x, right? If we find the partial y, this will be 2y. And from what we have learned, if we want to equaling this to 0, then at 0, 0, this is the best way that we get our critical point, right? And then the question will be asked that whether it's maximum or minimum, right? It's difficult to see. Well, it's definitely partial x is 0, partial y is 0, but it is critical point, but it is not maximum, not minimum. So not maximum, not minimum. If you check the graph, check with this color, red color, that is our 0, 0, right? And remember, we call this in chapter 12, this is called the saddle point. So now how to make this logically align with our definitions, and how do we define the saddle point in terms of the partial derivative? Okay, now we are going to move to what we call in this chapter the second derivative test. Okay, now let the function f is function of two variables with continuous second order partials in some disk centered around a critical point which have x0 and y0, and let we say we have another equation that we call D is partial x x and partial y y minus partial x y squared. D is from the determinant, so it's actually determinant of I don't think I have time to prove this, but let's say we have this D and we have this D. Then, okay, then if D is positive, and we have two possibilities when D is positive, either fxx positive or fyy positive. Maybe let me write xx first. Let me write this. This will be local mean. If partial xx negative, this will be local max. If D is less 0, now the x0, y0 is a saddle point. And if B equals 0, it's inconclusive. Conclusive. We can also check partial yy. Same condition. So when partial yy is positive, it's local mean. Partial yy negative, it's local max. But I think better to stick with just one. I think maybe just partial xx. That will be better. Okay, I think we can have some example. If you want to write completely this in the second derivative task. Okay. Okay, let's continue. Okay, I hope you can have. I think the important point is the the equations and what's happened when d is positive, negative, equals 0. That will be the main uh, the main point of this test. Okay, let's take some example. Okay. Example: find local max, local mean, saddle points of functions x4, okay, plus y power 4 minus 4xy plus 1. Now first, as usual, every time we have the function of two variables or three variables or multiple variables, the first thing we need to do is now, because we already learned on mostly partials, we can check the partials, okay? Partial x and then partial y. So first we can check the partial x, so step for partial x for x cubed minus 4y, and partial y is 4y cubed minus 4x. Okay, now we find the critical points. First we find the critical points. We find that we have x cubed minus y equals 0 and y cubed minus x equals 0. Now we can substitute either from x to y or y to x and solve the equation. So we can solve first, maybe finding this and solve to here. So we will have from x cubed, so we will have x9 minus x equals 0. So x8 minus 1 equal to, we can factorize this, okay? We can factorize through x4 plus 1. And we can further, every time we have the negative, we can factorize this negative. Okay. Now from here, we can have 3 real solutions. So x equals 0, x equal 1, and x equal negative 1. And then based on what we have, on y equal x cubed, so y will be 0, y will be 1, and y will be negative 1. So this will be all the critical points. Okay. Now next step is to check this critical point, whether it is maximum, minimum. Okay. Now we can check that with the partial, the second partial derivative. Okay. We are going to have, so first is we have this partial x. We are going to build on partial x. Okay. So we'll have 12x squared. Okay. And then partial y, this will be 12y squared, right? And then partial xy, this will be negative 4, and yx is the same as we mentioned earlier in the class. So we just need this three partial. Now remember, we have d is partial xx partial y1 minus partial xy squared. Okay. Now we can check the points. Okay, check the points. We can make a table if you want, if we would like, and I think it's helpful to have a table. So x, y, so 0, 0, 1, 1, and negative 1, negative 1. So this will be D, this will be F, xi. So we start with the 0, 0. So this will be, let me write, this is 12x squared, this is 12y squared, and minus, sorry, xy. So for 0, 0, this will be 0, right? 0 minus 16. So it's minus. So it's minus, then we can say that we don't really need the partial xx for this minus. Conclusions, here conclusions that 0, 0 is saddle. Okay, it's saddle point. And now for 1, 1, we can check 12, 12, it's 144, right? 144 minus 16. It's a positive, right? It's positive. But let's check partial xx is positive, or partial xx is positive. Maybe we'll write here positive. And the other one is positive minus, since it's also positive, but this is also positive, right? Positive. So positive, positive, what it means? Partial xx, if we look here, we'll have a local mean, right? Local mean. So we will have that the 1, 1 and negative 1, negative 1, both are local minimum. Now if we check the graph, how we are having these 3 points, we can have this graph. If we check that this part is the saddle, it is 0, 0, and this will be 1, 1, and this will be negative 1, negative 1. Okay. By the way, it looks like, you know, in like a cartoon, the Patrick, right, in SpongeBob, like a feet of Patrick. Right. Okay, that's the example. Okay, actually, in this 14.7, we have another uh, another example that uh, discuss about similar to what we have in optimization in calculus 1, but I don't think I will focus on more of that. Yeah, so whenever you have the exercise on this 14.6, I think you can skip that part. I will show you later which part that you can skip on. You can focus more on the analysis of graph, okay, finding the critical points, the second derivative, and then um, you need to make a conclusion which one is the saddle point, minimum, maximum. Okay, I think that will be more focused. Okay, and some of the I think last two question definitions. I think this is the absolute maximum and minimum for the definitions. Like I mentioned, I think the early definition for maximum and minimum. So we can tell the point which one is absolute maximum or minimum if we compare with the domain. If we compare with the domain. And this is the second derivative test that we have. If you would like to have more clear words. I think this is should be here. Here. Okay. So 14.7 is actually finished, but let me give you more examples. Here you can have one example, one more example, and then I will have a feedback for today. So let me give you one example. So the same questions, find local max, mean it has, and saddle points. If it has saddle points. Equations is f xy x squared plus y squared with e with power of negative x. And let me give you a couple minutes to see and try the question. Okay, now always to check the partial. Check the partial x will have a product rule, and then minus e x squared plus y squared, and then we can write 2x minus x squared minus y squared, and then e to the negative x, right? This is partial x, partial y. You just have 2y and then e power negative x. And then we going to have partial xx. We have another product rule, right? The product rule from here. We have 2 minus 2x, e power of negative x, and then minus e negative x, and then 2x minus x squared minus 2y squared. This will be equal to x squared plus y squared minus 4x, and then plus 2 e negative x, and then partial xy. This will be negative 2 y e or negative x partial y y. This will be 2 e negative x. Now if we have partial x equals 0 and partial y equals 0 to find our critical points, then we have 2x minus x squared minus, already we start from y, 2y e to the negative x equals 0, and from here we are getting the y equals 0, and substitute to 2x minus x squared minus 0, and this should be also 0, and from here we get x 2 minus x, so we are getting the x equals 0 and x equal 2. Critical points is 0 0 and 2 0, right? Now we are going to check the d for each one. We can have 0 0 2 0 d, this is x, this is y, and then f x x, and then conclusions. Okay. Conclusion for d will be partial x x, partial y y, and then minus partial x y squared. So we can first check the 0 0. So we check 0 0. First one is D00 is 4, right? It's 4, it's positive. If we check the YY, this will be 2, XX is also 2, right? If we check the, because all the things will be 0, so this will be positive, and this will be also positive, right? Partial XX is 2, right? Conclusions, this will be local minimum. And check the X equal to, this will be negative. When you put in 2, it will be negative, right? 2 minus 4, it's negative 2, so it should be having a negative. So we can know that this will be a saddle point. Okay. Okay, up until here, I also need your suggestion. If you have any suggestion regarding our class, how do we supposed to continue the lecture for the next? We have still at least until the second week of June, and we are focusing more on this month of May. We will focus more on multiple integrals, okay, and we will have the quiz next week for chapter 12 and 13. Okay, but I think to end our lecture, I would like to share the first is the QR code for our lecture. Let me just write the. Maybe I will wait for a moment here. If you finish this, we can move to our feedback session. Okay, I will wait for a few seconds. If you want to screenshot, you can screenshot. Okay, I believe should be clear. Let me stop this sharing and let me share the Google Chrome. Okay. Okay, please scan the attendance. Okay. If you haven't, we will have a play another game for our feedback. So I hope you are ready. Okay, I will go through this. Okay, wait, reload. Okay. Okay, if you are using your phone for the WebEx, then you can maybe go to your browser and go to dementi.com and using the code. I believe this will take on around 6 to 7 minutes. We have I prepared for 4 questions. Okay. Okay, are you ready now? Okay, let me wait for a while. Okay, I believe we can start. Okay, waiting for the players. Okay, we have six players. These 6 players. Okay, other would you join the feedback sessions? The other students. Okay, anyway, let me just start the countdown. Okay, first question. Okay, true or false, just checking true or false for okay, it's actually true. It's actually true. It's the same thing as we did before, but it's changed the some terms, but it's actually the same. Okay, next question. Okay, who will be the one who are getting? Okay, Gustav. Okay, I think can rename if you want. Okay, Carl Gustav. Okay, next question. Okay, get ready. Okay, 3, 2, 1. A lot of words, but it's actually quite simple. It's actually quite simple. The calculation is quite simple. You need to find the first derivative of p at t equal to. So this is related to the chain rule. Okay, 30 seconds. Okay, 22, 20. Okay, 10 seconds. 3, 2, 1. Okay. Okay, congratulations. Correct answer 42. Okay. Okay, next question. Get ready. It should be a true or false question. It should be false. Remember, gradient factor is factor. It's not scalar. Okay, so it is 0 and then 1 over 1. Okay, good, good. Oh, cargo stuff. Okay. Okay, last question. Okay, find the directional derivative of the function with the given point with the direction of vector phi. Vector phi we have there. Don't forget to use the unit vector. Okay. Unit vector. The number is actually quite good. The number is good. If you calculate, it should be a good number. Okay, 5, 3, 2, 1. Let's see. Yeah, it's actually 1. Okay, so congratulations, only one student got correct. Okay. Oh, still. Oh, the cargo stuff. Okay, so congratulations. But one last survey. This is just my thought. Okay, so we can have all online class until the end of the semester, but exam should be offline. So every quiz, every exam will be offline, or we have offline class as usual, or we may take one part offline, one part online. Okay. Well, maybe I will give you more uh, survey later on to check whether we need to have uh, all online class or offline class, or both, like maybe Tuesday online and then Thursday offline, because I prefer for TA to be offline so that you can have uh, more energy to discuss with your TA or having more exercise. QR code, yeah, later. Okay. Okay, wait. Here, QR code. Okay, okay. Finish for attendance. Anyone finish the QR code? Let me check again. Okay, I think for 8 students who joined the survey, you prefer online classes. Okay. Okay, I will consider online class. But I will give you more questions or survey later on. Okay. So for now, we end our class today. I will give you announcement for some additional video that I already upload in YouTube. That is about the chapter 14 and session on 14.8. So I will just make into just additional video for the Lagrange multiplier. So I hope you can watch the video later on. Okay. So see you later, and stay safe. Okay. If you feel any discomfort and maybe some symptoms, please let me know, and you don't need to come to the class. Okay. 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 See you later.